In this video, I'm going to present the derivation of the 1D shallow water equations, which are used to model open channel flow. In this context, shallow water is defined by flow in which the depth of the water is small compared to the horizontal reach. This is typical of channels such as canals, rivers, and streams. The length of the channel, labelled as L in the diagram, is much greater than the depth of the water in these cases, labelled H here. Before we proceed, we note that the fundamental equations of fluid flow are conservation laws: conservation of mass or matter, energy, and momentum. Regardless of the nature of the flow, the fluid motion is subject to these three laws. Here, we are going to use conservation of mass and momentum to derive the shallow water equations. We'll derive them here in one spatial dimension, which we'll take as the x direction. So, we'll use a control volume of fixed width b and the channel bottom as its base, and the free surface of the water as its top. Now, because we're only working in one dimension, we only have a single value of depth at any position on the x-axis. That is, we assume implicitly that the depth of the fluid doesn't vary across the width. We denote the depth as h, and for the purposes of our derivation, we'll assume that the control volume is of infinitesimal length dx. We need also to take account of velocity or discharge because we're interested in flow. So let's denote the average velocity over the left-hand control surface, the flow into the control volume, as u. We'll take h and u to be our dependent variables, meaning that h and u are both functions of the two independent variables x and t. It's worth noting here that in general, if we have a variable y that's a function of x and t, then at fixed time t, the change in y as we cross the control volume, i.e. as we go from position x to x plus dx, is given by dy equals partial dy dx times dx. Equivalently, we can say that the value of that variable on the right-hand side of the control volume is given by y plus dy by dx dx. We'll use this relationship in our derivation to define the mass and momentum out of the control volume. This will, of course, be true for h and u, so we have to be careful here. The way this is illustrated implies that the depth of the water on the left and right-hand side of the control volume are equal, when this may not be the case. Remember, the top of our control volume is a free surface, and in general, the depth on the right-hand side of the control volume will differ from the depth on the left. That difference in depth will be dh by dx dx, and similarly, the average velocity out of the control volume will be u plus du by dx dx. Now, we're dealing here with conservation laws. If a variable is conserved, then we can state that the accumulation of that variable within a control volume, be it mass, energy, or momentum, must equal the amount entering the control volume minus the amount leaving. So let's start with mass. Let's think first about the control volume itself. We are ultimately going to integrate, allowing dx to tend to 0, so the control volume v can be evaluated simply as its width b times its height, which is the water depth h at position x, times its length dx. Thus, the mass of the fluid within the control volume is ρ bh dx, where ρ is the fluid density. The accumulation of mass in time dt can be written as dm by dt times dt, which equals d by dt of ρ bh dx times dt. Because mass equals ρ bh dx, the amount of mass entering the control volume in time dt is going to be ρ bh dx dt times dt, which can be written rho bhu dt. And the amount leaving will be rho bhu plus d by dx of rho bhu times dx, all times dt. We can now equate the accumulation of mass in time dt with mass entering minus mass leaving, giving this equation. We can see that two of the terms on the right-hand side, rho bhu dt, are equal and opposite, so they cancel out. And, dividing throughout by dx and dt, we are left with the equation d by dt of rho bh plus d by dx of rho bhu equals 0. Now, if flow is entering the control volume from elsewhere, for example when we have a natural channel with flow running into the channel from a floodplain, then we need also to consider this additional mass flow. We call this lateral inflow, and we need to add it to the mass entering term. Defining QL as the rate of volume flowing into the channel per unit length of the channel, we have the mass entering in time dt equals rho bhu dt plus rho ql dx dt. The accumulation in this case becomes this. Again, the rho bhu dt terms cancel, and we can divide by dx dt, yielding d by dt of rho bh plus d by dx of rho bhu equals rho ql. For an incompressible fluid, such as water, the density ρ is constant, and we have d by dt of bh plus d by dx of bhu equals ql. Noting also that the area of the cross-section A is bh, and that the discharge q is area times average velocity, then we can write this equation as dA by dt plus dq by dx equals ql. Okay, so that was mass. Now we move on to momentum. For now, we will assume there's no bottom slope, i.e. that the channel bottom and hence the base of the control volume is horizontal. First, we note that momentum is defined to be the product of mass and velocity, which for our control volume is rho bhu dx. Thus, the accumulation of momentum in time dt is given by d by dt of rho bhu dx dt. Next, we need to consider the momentum entering our control volume in time dt. We have to be careful here as there are two components. The first comes directly from the motion of the fluid and is rho bhu dx by dt dt, which gives rho bhu squared dt. The second is a result of pressure forces. Here our shallow water approximations come in. Remember that we consider only a single value of the horizontal velocity u, ignoring the variation of velocity with depth. This approximation is never true, but is a reasonable approximation when the depth is relatively small. This implies that pressure gradients are due only to the displacement of the pressure surface, and we assume a hydrostatic pressure distribution, the linear distribution illustrated here with gradient ρg. This results in a horizontal thrust of magnitude a half rho g bh squared. If this isn't familiar, you can find details and derivations in my YouTube videos on hydrostatic pressure and hydraulic thrust on plane surfaces. We also know from Newton's second law of motion that force equals rate of change of momentum. So the pressure force contribution to the momentum entering the control volume is a half rho g bh squared times dt. Thus, the total momentum entering the control volume is rho bhu squared plus a half rho g bh squared, all times dt. Now, as before, we can use this to generate the momentum leaving the control volume, giving us this expression. Equating accumulation in time dt with momentum entering minus momentum leaving, we have this equation. As with the mass equation, the amount entering terms cancel out, and dividing throughout by dx dt, we have d by dt of rho bhu plus d by dx of rho bhu squared plus a half rho g bh squared equals 0. For an incompressible fluid such as water, rho is constant, and thus we have d by dt of bhu plus d by dx of bhu squared plus a half gbh squared equals 0. Okay, so we have the momentum equation for shallow flow with no bottom slope, but in general we need to consider a change in slope across the control volume. The work we've already done is still valid, but when there's a bottom slope we also need to account for gravity and friction forces. So let's assume that our control volume looks like this, with the bottom slope at an angle theta to the horizontal. We assume that theta is small, ensuring that the velocity remains approximately horizontal. We will have a gravity force acting down the slope and a friction force acting in the opposite direction. Our accumulation equation now looks like this, where you can see the momentum due to those two forces has been added to the right-hand side of the equation. As before, we have some terms that cancel, and dividing by dt, we are left with this equation. Unravelling this further, the gravity force is mass of the control volume, rho bh dx, times g sine theta, and the friction force is p tau dx, where P is the wetted perimeter and tau is the wall shear stress. Thus, we have this equation. And dividing throughout by dx, we have this equation. The terms on the right-hand side are known as source terms due to the bottom slope. We can simplify this by noting that if theta is small, then sine theta is approximately equal to the bottom slope S0. We can tidy up the source terms further by introducing the notion of a friction slope SF, which we define to be tau over rho gr, where r is the hydraulic radius, defined as the ratio of the cross-sectional area A and the wetted perimeter P, which in the case of a rectangular channel is just BH over B plus 2H. Now we have P tau equal to rho BH times SF, and the right-hand side of the momentum equation simplifies to rho BH times S0 minus SF. For an incompressible fluid such as water, we can divide throughout by rho, and this yields the equation shown here. Thus, for an incompressible fluid and a shallow slope, we have this pair of equations describing the relationship between the dependent variables depth h and average velocity u. Dividing both equations by the width b, we get the equations written in what we call conservation form or conservative form, as shown here. These equations can be written in terms of different dependent variables, such as cross-sectional area, average depth, discharge, or unit discharge. These different forms are derived in my accompanying video, 1D shallow water equations in different forms. That's all for now. Bye.